a little bit of review. You guys covered solution chemistry, or at least chemicals in water. In Chem 200, well, we're going to look at the quantitative information here in this particular course. So remember that solutions are nothing more than a solvent, a solute, and together it's called the solution. A true solution is homogeneous, which means that the solute is mixed in and no solid residue is left behind. If there's any solid residue that doesn't dissolve, then it's not homogeneous anymore, because if you look at one part of the solution and another part of the solution, it's not the same. A true solution, of course, is going to be somewhat transparent unless it's really concentrated, but generally the true solutions are transparent because the solute dissolves or is hydrated by the water at the molecular level. Okay, you might assume that you already know something about solutions, that it has the solute and the solvent, but that's a common mistake that you will make when you're doing concentration calculations, because you got to look at the concentration unit, and if the concentration unit says moles of solute over liters of solution, a lot of times you will think that liters of solution is just liters of solvent. And it's not just a solvent, it's not just water, it's actually the volume occupied by the solute that you add and the solvent that that it's dissolving in. That's the reason why, okay? It's the reason why I get these messages. Sorry about that. That's the reason why when you prepare a solution, you usually use this item over here called a volumetric flask, because a volumetric flask is one glassware in which there is a calibration mark that tells you the exact volume. So if you want 1 liter of solution, you add first the solute and then you fill it up with water. You don't put in 1 liter of water, because 1 liter of water plus the volume of the solute will be exceeding 1 liter of solution. So what you do is you weigh the solute, and you pretty much know how much to weigh if you know what concentration that you guys are going to be determining, or what concentration is required for the solution to prepare. You put all of that into a container, and then you add some water. In this class, the solvent we are going to be using is water. It's going to be aqueous solutions, okay? Unless otherwise stated, it's an aqueous solution. If you go into organic chemistry, then it might be methanol, it might be acetonitrile, it might be benzene. But for the most part, if you were in lab, we don't do that. Now, if you're doing a work problem, yeah, we could use different solvent other than water, because you need to know how to do those calculations. But for the most part, if you are in general chemistry, we don't use any type of solvent other than water. So most of the solutions we are going to be using is aqueous solution. Anyway, you add water, you make sure it's distilled water, not tap water, because tap water has a lot of impurities in it, and it just messes up your solution. But you add distilled water, and then you add so that you start dissolving the solute. You shake it like you see in this picture, so that all the solute dissolves, and then you slowly add the solvent so that the meniscus is right at the calibration mark of that particular glassware. Okay, so it's typically what you guys would be doing if you were in lab. Now you just have to kind of like remember it and kind of see how it's done. Anyway, solutions generally have 2 components. Together it's called the solution, but the solution that you know, like salt water, solid sodium chloride in water, is just one of 9 possibilities. You can actually have a gas in a gas, like air. That's a solution. The minor component is going to be like oxygen. The major component is nitrogen. And of course, there's a lot of other impurities in there. You could have alcoholic beverage, ethanol in water. You can have jewelry, like silver in gold, and depending on the percent of gold in that particular jewelry, then it's defined as a carat. So 24 karat gold is pure gold, but 12 karat gold, well, if you get a 12 karat gold and it's an engagement ring, you give it back to your fiance. They're pretty much being cheap. Okay, it's only 50% gold. So again, solutions is made out of two components, but it has to be homogeneous. You can't see any signs that it's a mixture. Okay, only that it's uniform throughout. Here is just example of how to calculate molarity or how to prepare a solution. And you guys already covered molarity in Chem 200. It's the moles of the solute. So that means that if you have the mass of a solute, you can, and you know the identity of that solute, then use the molar mass and the mass to get the moles, and then you divide by the volume of the solution. So this is an example of that. In this particular case, we've got copper sulfate pentahydrate. Now, when you see this formula, copper sulfate pentahydrate, you guys should be able to translate that to a chemical formula. Why? Because you need the molar mass. So copper is +2, sulfate is -2. So of course the formula is going to be CuSO4. And then this little thing right here is the hydrate. It means that there are 5 waters that is hydrated to the copper sulfate, because copper sulfate is sort of hygroscopic, so it attracts water. So what you need to do is, when you count this little dot's not a multiplication, it's an addition. Water has a molar mass of 18.0 grams per mole. So what you need to do is multiply 5 times 18, and then 1 times sulfate is about 96 grams per mole, and copper is about 63. So this is your sulfate, this is your copper, and this is your 5 waters. So to get the molar mass of this particular chemical, and that's the chemical that you're getting from the lab, you need to add this up. A lot of times, especially beginning chemistry students, they don't know what to do with that hydrate. They think they need to multiply it by 5, or they tend to ignore it. The chemical that you see right here has 5 waters in it. So the molar mass of that chemical is going to be 249.6. Now, if it was anhydrous and it didn't have the water, then you would just use the molar mass of copper sulfate, no waters added. But the fact that it's a hydrate, it means that these crystals already contain the 5 waters. Anyway, what you do next is you figure out the moles of 249.6, which comes out to 0.1. Okay, and you, of course, divide it by the volume, and that'll be the concentration. This particular problem, I think, is you want to prepare 0.1 moles, 0.1 molar solution in 1 liter. So you sort of work backwards. Okay, you sort of work backwards. And this particular problem is, how much do you need to weigh of that copper sulfate pentahydrate in order to get a 0.1 molar solution? So this right here, this calculation right here, is the calculation you would use. Start out with the concentration you want. You use the molar mass, the volume that you're going to prepare, and that will tell you how much you have to weigh out. So hopefully that's a review, because that's what you guys did in Chem 200. If you don't remember that, the stoichiometry or the dimensional analysis that you need to employ, then please go back and review that. So this just tells you, it gives you a description of how to prepare these solutions. And again, that's one of the skills that you guys will have to, would have learned and will know how to do on paper because you're taking the lab. Okay. So there are many ways of expressing concentrations. Concentrations is a way of expressing how much of the solute you have in the solution. Okay, and remember that the solution is the solvent and the solute. So concentration is a way of expressing the solute in that particular solution that you are handling. And there are many ways actually. We're looking here at the 5 most popular ways, at least the most popular way in terms of this course. Molarity, we already covered. That's moles of the solute over the volume in liters of the solution. Remember, I said solution, not solvent. So you gotta remember how these things are defined. Molality. Now these two can be different, can be confused because molarity is spelled with an R. Okay. Molality is spelled with an L. Whenever you hear molality, it's the moles of the solute, but it's the kilograms. It's the mass of the water. It's not the solution. It's the solvent. Okay, it's in kilograms. So keep that in mind. Because volume sort of expands and contracts at different temperatures, whenever you're dealing with temperature sensitive material, you got to express the concentration in terms of molality, because the molality of a solution is constant because mass doesn't change just because you heat it up or cool it down. But molarity will change with temperature because the volume of anything tends to expand when you heat it up and tends to contract when you cool it down. So please keep that in mind. Concentration by parts. I like to call it concentration by parts because it's really the solute and the solution. The mass of the solute over the mass of the solution, or the mass of the solute over the volume of the solution, or the volume of the solute over the volume of solution. So we're looking at the different parts. And if it's a percent, then you multiply that quantity by 100. But sometimes, because the concentration is so low, we don't multiply it by 100. We multiply it by 1,000,000. And when we multiply not by 100, but by 1,000,000, 1 times 10 to the 6, then the new unit is called ppm, or parts per million. Or if we multiply by 1,000,000,000, 1 times 10 to the 9th, then the unit that we express that concentration in is ppb, parts per billion. But if you know how to calculate percent, it's a no-brainer in terms of expressing it in ppm, because all you're doing is changing this multiplier from 100 to 1,000,000 or 100 to 1,000,000,000. That's the only thing that you are doing. You're taking the solute over the solution, whether it's mass or volume, volume or volume. You're taking that ratio and you're multiplying it by 100, 1,000,000, or 1,000,000,000. So it's not hard to do those types of calculations, and you're not learning anything new. Okay, it's just a way of expressing very, very small numbers. And when you take very, very small numbers and multiply it by a huge number, then it becomes significant. And that's what scientists do. They like to do that to point out to the general public that this concentration, this poison, is not insignificant. It's significant. And so by making it a larger number with not so many zeros, people will pay attention to it. There's the mole fraction. We covered the mole fraction in gas laws. Okay, you guys covered that in gas laws. It's the moles of the solute over the moles of the solution. So in order to get the moles of the solution, you need to know the moles of the solvent. You need information about the solvent and the solute. So that's your mole fraction. And then finally, we have normality. Normality is the number of equivalents per liter of solution. The number of equivalents is defined by the chemical that you have, and it's very related to the moles of the solute. If you know the moles of the solute and you know the formula, you can convert that to numbers of equivalence. Take, for example, sulfuric acid. Sulfuric acid is H2SO4. The chemistry of sulfuric acid, when we put it in water, is 2 hydrogens, and then the sulfate stays together. But for every 1 mole of H2SO4, we produce 2 equivalents of hydrogen. That's your conversion factor. See how this conversion factor is defined by the formula? That's why you need the formula to figure this out. Now if you have a 3.0 molar solution of sulfuric acid, and you want to figure out what the normality is, N, then all you got to do is use this conversion factor. For every 1 mole of sulfuric acid, you've got 2 equivalents. So 3 times 2 is 6 normal. Okay? So it's not difficult to convert a molarity to a normality, but you need the formula. Sometimes we don't have, let me clear this slate. Sometimes we're not looking at hydrogen, although normality is used a lot in acid-base chemistry. Sometimes we're looking at charge. Okay? When we have aluminum chloride, we have aluminum, which is +3, and 3 chlorides. So for every 1 mole of aluminum chloride, we have 3 equivalents of aluminum charge. And the reason why we have 3 equivalents is because we're looking at the charge of the species. Okay? So whether we're talking about acid-base chemistry, in which we're looking at the number of hydrogen an acid has, or an ionic substance, in which we have a positive and negative, and we're looking at the charge of the specific ion, then you can express concentration in terms of normality. But you need to know the formula, and you need to know the charge. Okay? So that's why I said that these concentration units are not difficult if you already remember the fundamentals, and the fundamentals is molarity, because you guys can express. In fact, that's what you do in lab today. What you will be doing is, for those of you in lab, you'll be given part information of the solute and the solvent, and then you're going to express it in terms of mole fraction, in terms of molality, in terms of percent concentration. You guys are going to be doing that just based on the information that's provided. And what information do you need to make many of these conversion? Well, you need information about the solute. And if you have the moles and you know the chemical formula, you can figure out the mass through the molar mass. Okay? The moles of a chemical and the mass of a chemical is related through its molar mass. And you also need information about the solvent. And the solvent is, in this particular case, water. So if you know the moles of water, because of course you know the formula of water, then you can calculate the mass. The other thing that you could do is you could also, from the mass, figure out the density. Okay? Because what is the density? The density is the mass of that particular substance in the volume it occupies. So sometimes if you need to calculate the volume of the solvent, the way you calculate the volume of the solvent is through its density. You can see it right here. Okay? You use the mass and then the density as the conversion factor to get the volume. So you guys are using a lot of the chemistry 200 that you learn, and you're using a lot of dimensional analysis. Okay, using a lot of dimensional analysis. So let me go ahead and clear this real quick. So I want to talk about this in more detail. And then we'll do examples. Okay, do examples, and that's all I really want to cover in this, and then we'll go back to chapter 11 if we have time. But here's mole fraction. Mole fraction, of course, is going to be the moles of the solute and the moles of the solution. So you need the moles of the solute right here. And then together with the moles of the solvent, you can calculate the mole fraction because it's the moles of solute over the moles of solute plus solvent for that. Molality is expressed by small m, okay? Molality. It's the moles of the solute and the kilograms of the solvent. So if it's grams, if you're given like 45 grams of water, you gotta convert 45 grams to 0.045 kilograms, and then you can express that concentration in terms of molality, okay? By the way, if the density of the solution equals the density of water, then the mass of the solution is equal to the liters of the water added, because they're practically the same. 1 liter is 1,000 grams is 1 kilogram if that solution has a density of 1. And generally a density of 1 is going to come not from pure water, but from a solution that is very, very low in concentration, like 0.01 molar or 0.005 molar. Those concentrations with very, very, very little solute will practically have the same density as just the pure water, because the minute solute that you add doesn't really add to the mass of that total solution. So that's a quick hint that you guys could use when you do these calculations. When you see that the mass of the solution or the concentration is very, very small, then the density of that solution is practically 1, okay? Percent is going to be the mass of the solute, mass of the solvent. The solvent and the solute together will give you the mass of the solution, but those are two information you need to get percent concentration. If you know the mass and the volume of the solvent, you actually need the volume of the solution. Then you can get the percent concentration. And we usually express this in terms of MV, meaning that the numerator is mass and the denominator is volume. So that's how we express in terms of knowing what we are using. Molarity is down here, and the reason why molarity is down here is because we actually need the moles of the solute, and then we need to take the mass of the solute and the solvent, use the density to get the volume. So this is a quick flow chart on how to do these calculations, and it looks simple, then it looks confusing, but you need to practice it and learn how to navigate here in order to be skillful in doing that. And that's what today's lab's about. Okay, here's a better chart on how to do this. This is from a different textbook, but basically tells you the same thing. Okay, so here is a problem. It says that we have 3.5 grams of cobalt chloride is dissolved in water to produce 100 ml solution. Now, 100 ml of solution means that the 3.5 grams plus the water adds up to 100 milliliters. Now, you don't know the volume of the cobalt chloride, so we're going to have to give you some other information, like the density, so you can calculate other concentration units. So what we do here is we tell you that the density of the solution is 0.95 grams. So I want to show you how to calculate the molality, the molarity, the mole fraction, the percent concentrations, the ppm, and the normality of the cobalt for this particular solution. So let me go ahead and get a blank screen. And then the other thing I need to do is I need to look for this information on my other screen, because when I do a blank screen, I'm going to lose that information and I don't want to keep going back and forth. Okay. So I have it in my second monitor. Let me go ahead and clear this. So we have 3.5 grams. Maybe you can work ahead if you want, but this is just an example. And of course, this is being recorded by Zoom. By the way, let me just warn you, whenever you go to these Zoom meetings, it's automatically being recorded. I found out a long time ago, if I just automatically record it from the beginning, it's easier to chop information that I don't need rather than go through a whole lecture and forget to turn on the recording. So I just set it for automatically recording whenever we have a Zoom session. Okay, you guys don't need to put your face on the video if you're sensitive to that, but it's just a good practice for me to get these recordings done. That way I don't forget. So like I said, this is going to be recorded in Zoom, and you can tell because there's a recording button in your screen and it's blinking. But we have 3.5 grams of cobalt chloride. Let me go ahead and do this. The molar mass is 129. And usually I give you the molar mass, unless I'm being mean, then I let you guys calculate that. Is that, and it's dissolved in 100 milliliters of solution. So we basically have a volumetric flask. That right there is 100 milliliters of solution. And we're adding to this, that little glitch right there is 3.5 grams of cobalt chloride. Now, based on these two information, you guys can calculate the moles. Okay, based on this information right here in the mass, you can calculate the percent, concentration, mass per volume. So right away you have information without hardly doing any conversion to do some of these. But let me go based on the order of the question. If you have the lecture notes, you can go to Canvas, go to Unit 1, and go to Chapter 13.1, since your screen doesn't show it, and open up that PowerPoint file to find this page. That way you can follow along. Okay, let's figure out the moles of cobalt chloride. We have 3.5 grams of CoCl2, and we know that I assume that the molar mass is correct. Again, dimensional analysis. I have grams up here, moles down here. I'm going to put grams here, moles down here. It's 129.93 grams per mole of cobalt chloride. And then doing that calculation, we just do the math, 3.5. And you guys should do the calculation with me, because whether I'm here sitting at home talking to you or in front of you on a blackboard, I've been known to have punching errors. So it's good to have you guys double check. So this is 2.694 times 10 to the minus 2 moles. What I usually do, and what's good practice, is to write down as much of the information, significant figures, in your intermediate calculation. In fact, just keep it in your calculator and do your subsequent calculations. That way you avoid rounding off errors. The 100 milliliters, of course, you guys can do this off the top of your head. It's 0.100 liters. So right away we know the molarity. The molarity is going to be 2.694 times 10 to the minus 2 divided by 0.10 liters. So this is moles. And so that's just, in this particular case, 2.6, and we're looking at two significant figures. Oops, that's the problem with this. whenever I switch, and that was an accident, sorry about that. Um, Whenever I switch screens, it just blanks the screen. But if I remember correctly, okay, the mass of my cobalt chloride is 3.5 grams. We had 100 milliliters. This goes over to 2.694 times 10 to the minus 2 moles. And so between these two, my molarity is going to be 2 point, and we're looking at two significant figures. So 2.7 times 10 to the minus 1 molar. Okay, so that's the first one. The molarity is 2.7 times 10 to the minus 1, or 0.27 molar. Now let me calculate molality. Molality is the moles of the solute, which we said was this right here, over the kilograms of water. Now we don't have the kilograms of water because what we have is 100 milliliters. And that right there is the mass of the, that's the mass of the water, and or the volume of the water and the volume of the cobalt chloride. But we do have the density, and the density of the solution, rho, Greek symbol rho, is the symbol for density, for those of you who took physics, right? The density is 0.95 grams solution. Now it's very important to label these things because you could easily have the density of water or the density of cobalt chloride, but this right here is the density of the solution. So I'm putting 0.95 grams of solution over 1. Remember that density is grams per milliliter. Grams per milliliters of solution. So we can use this information together with the volume to determine the mass of the solution. Why do we need the mass of the solution? Because the mass of the solution now tells us the mass of the cobalt chloride plus the water. And if we know we have the cobalt chloride right here and we subtract that out, then we have the mass of the water. So let me show you how that's done. Okay, we have 100 milliliters of solution. Notice I am carrying my label, because if you don't carry your label, you're going to easily get confused. And then I'm going to use the density. See how I have solutions here? That means I'm going to have 1 milliliter of solution down at the denominator of my conversion factor, and I'm going to have 0.95 grams of solution here. Not grams of water, but grams of solution. So if I do this, 100 times 0.95, that's just 95 grams of solution. Why is that important? Because 95 grams of solution equals 3.5 grams of cobalt chloride plus the grams of the water. Now that's how I calculate the mass of the water. So I take 95, subtract 3.5, and I get 91. So the mass of the water equals 91.5 grams. Now I can take that to get the molality. The molality right here is the moles of the solute, which we said was this right here. So the molality is equal to 2.694 times 10 to the minus 2 moles over, it's 91.5 grams, but I have to convert that to kilograms, so it's 0.0915 kilograms. 0.0915 kilograms. And if I do that quantity right there, okay, then I should be able to calculate my molality. So I'm going to punch in 2.694 to the 2 negative and divide by 0.0915. Again, because even though we have 95 grams of solution, when we subtract off the cobalt chloride, that comes out to 91.5 grams, but we have to express it in kilograms. So that comes out to The molality of this particular solution is going to be 0.29, I apologize for running out of real estate, 0.294 m. So let me write it over here. 0.29 small m for molality. Now, I'm going to take a step back because I want you to see how the molality and the molarity, they're not the same. Reason why they're not the same is because the density is different for water. If the density was 1, the molarity and the molality would be the same, okay? It's a quick hint. The fact that they're very close should tell you that the density is near 1. And in fact, whenever you do a molarity and a molality calculations, these two units should be very close to each other. They won't be identical unless the density of the solution is 1. But depending on how dense the solution is, how close it is to 1, those two numbers will be very close to each other. If the density is really off, like 0.5, then those two numbers will be like half off. Just a quick hint as you do more of these things. Yeah, there's a button in the bottom here that's blocking the numbers here. That's why I'm rewriting it over here. Okay, because I'm running out of. I have a very small iPad. So that's let me clear this. Okay, let me clear this, and then we'll work on mole fraction. In the meantime, I need to take a picture of this. That way, I'll remember this information because I need to remember 2.69. Let me just clean my slate here. Okay, I'll just clear this all up rather than switch back and forth. And the reason why I need to clear this is so that I don't lose information as I continue on with this problem. So the molality equals 0.29 m. The next part of this particular problem is calculate the mole fraction. Mole fraction is moles of the, that's m, moles of solute over moles of solution. Well, we know what the moles of the solute is. It's this right here, okay? It's 2.694 times 10 to the minus 2. The moles of the solution is going to be 2.694 times 10 to the minus 2 plus the moles of the water. We don't know the moles of the water, but we certainly know the mass of the water, which was 91.5 grams of water. That was the mass we calculated, because remember the mass of the solution is 95 grams, and the mass of cobalt chloride is 3.5. So when you take 95 and subtract 3.5, you get 91.5 grams of water. All we got to do now is use the molar mass of water, which is 18.0 grams per mole, and that'll give us the moles of the water. So let me go ahead and do that in my calculator. See, these concentration conversions, they're not as easy as you might think. It takes some work, but the work that you're doing is stuff that you guys already know how to do if you learn Chemistry 200. And guess what? Dimensional analysis is your friend. That's how I work all my problems, is I always let the units, because I don't want to memorize these formulas. I just let the units figure it out for me. 91.5 divided by 18, that's going to be 5.08 moles water. Let me try that again. 91.5, 18. Yeah, 5.0. Now I get 5.05. Try that again. Yeah, 5.08. Okay, so what is the mole fraction therefore? Put this in here and then we calculate it. So we take 2.694 and to the 2 negative, and we add to that 5.08. That comes out to 5.1069. Again, I'm writing as many significant figures as my calculator shows. Actually, could write more. That way I don't have rounding off errors in the end. 2.694 to the 2 negative. And remember, this fraction right here, you don't multiply it by anything. This fraction should be less than 1. If it was 1, you've got a pure substance. If it's less than 1, it's a mixture. This particular case is 5.27 times 10 to the minus 3. So my mole fraction here using 2 significant figures. Again, why am I stuck with 2 significant figures right here? You always look at the original data, because the original data is going to limit the number of significant figures your answer will contain. So this right here is 5.8, 5.3 times 10 to the minus 3. That's my mole fraction. Okay, yeah, 5.08, thanks, Justin, on checking my math. So that's the mole fraction that we have in this. So we've calculated molarity, molality, and mole fraction. I'm going to clear this. And again, it's okay because it's all being recorded. So if you go to the recording, you can see all of this. But I don't want to blank my slate here, because then this information that I calculated previously is going to be lost. So let me go ahead and do the next one. The next one is percent concentration. This is probably the easiest. We know that the solution is 95 grams. So percent by mass, sometimes we write it m/m, is 3.5 over 95 times 100. Now, you might say to yourself, but I thought we had 100 milliliters of solution. Yeah, we have 100 milliliters of solution, but the solution only weighs 95 because the density is 0.95 grams per mil. Okay? So please keep that in mind. This is the mass of the solution. This is the mass of the solute. And so if we do that, take 3.5 and divide by 95, and multiply by 100. That way we get our percent. This is a 3.68% or 3.7% solution. Guess what? If I take this and I multiply by 1,000,000, okay, I take that number, 3.5, divide by 95, and multiply that number by 1,000,000, then I've got 3.7 times 10 to the 4th ppm. That's what you guys should get. And if I multiply that by 1,000,000,000, okay, then that's 3.7 times 10 to the 7th ppb. And that's all you're doing in expressing these things in ppm or ppb, is you're changing this multiplier right here from 100 to 1,000,000 or 1,000,000,000. It's that easy. Okay, it's that easy. So don't make it harder than it is. It also asks us to calculate the moles, the percent M over V. That one's easy. That's just 3.5 over 100, because the volume of the solution is 100. So that's 3.5%, or 3.5 times 10 to the 4th ppm. And then you need to say M over V to express that it's a mass volume conversion. Okay, so the last one, so I'm gonna erase part of this, you guys get the idea, is normality. The normality is the last one. And normality, you have to look at the formula. So what we have is cobalt chloride. You guys know that the fact that chlorine is -1. And you know chlorine is -1 because it's a halogen. Halogen needs one more electron to get an octet. So its most stable charge is -1. The fact that you have two chlorines means that cobalt is +2. So the conversion factor is for every 1 mole of cobalt chloride, you have 2 equivalents. Okay, so remember the molarity was this. So we're going to use that 0.27 moles per liter, per liter of cobalt chloride. Then we're going to use this conversion factor right here. For every 1 mole of cobalt chloride, we have 2 equivalents of cobalt. So our normality in terms of the cobalt is just 0.27 times 2. And that is, of course, 5.4. 0.54 normal. So that's how you do this type of calculation. When you're given some information, you have to use the knowledge you have of these chemicals and dimensional analysis in order to go through the different calculations. So these are my answers. The normality is that the percent, M per M, the M per V is 3.5. Okay, the mole fraction is that, the molality is that, the molarity is that. So hopefully you were able to follow along. Go back in here. You guys know how to do this. Go back in here when you, for those of you, especially in lab, and you need to do these calculations. Got to go back to the how these concentration units are defined, because that's what you need to do in order to work these problems. So I'm going to clear this. Okay, and here are some of the solutions. Okay, so yeah, it's good. The lecture notes have this information. So anyway, that's more examples shown right here. You can walk through it. I won't go through that. This is something I would come up and do in class because it's so pertinent to what happens when you drink and drive. The BAC is the blood alcohol level. And in California, it cannot exceed 0.08%. There's actually an extra credit problem in the discussion that I will release later on, where you guys will calculate, because each one of you will have a certain body mass. And if you have a certain body mass, that means that you have a different blood volume. Okay, bigger people is going to have a larger blood volume than smaller folks. So you can actually calculate, depending on the percent of alcohol in the beverage you consume, your blood alcohol level after consuming 1 beverage or 2 beverage. So there's an extra credit problem that I will post in the discussion board, and you guys need to show your calculation and then figure out what your BAC level is after 1 drink, after 3 drinks, after a 6-pack. If you're drinking beer, or if you're taking shot, after 1 shot, after 3 shots, after 6 shots, okay? And the reason why, and what you will remember, of course, is that beer has a usually 4% alcohol level, whereas shots, generally 40%. So when you're drinking shots like tequila, you're drinking a smaller volume. If you're drinking 12 fluid ounces of tequila, that raises your blood alcohol level pretty fast. Anyway, there's a problem that is in the discussion. And this right here gives you a walkthrough of how that's done, okay? The rest of this, like this right here, is just some interesting statistics. in terms of what happens when your blood alcohol levels between 0.03 and 0.06. You basically lose your concentration. You have mild euphoria. You tend to be relaxed. That's probably the state that most of you want to be in. But you don't stop there. Just continue on. And what happens is that then you have disinhibition. You have extroversion tendencies. Your depth perception is gone. You have glare recovery. And then if you continue to drink, eventually you will die. Anyway, I just thought I'd show you this because certainly chemistry is not isolated to the textbook. It actually has real life examples. So the rest of this is just more or less more calculation. And I really want to keep our session to about maybe an hour. And then, so you guys can look through this and look at some examples and do some problems on your own. And then the rest of the time, I will answer questions that you might have and use this session to kind of like go over questions or problems you might have. And if there's no other questions or things like that, then we'll go ahead and excuse. We never got a chance because I got carried away. I tend to do that in some of my discussion. I tend to go off on a tangent. So we never got a chance to go back to chapter 11. So next time on Monday, I'll do a quick review on chapter 11, at least the pertinent information. Okay, so that's where we're heading to on Monday, but I really wanted to cover this and this particular example. That way, for those of you in lab, you'll see how these types of calculations are done. So if you guys have any questions, you can do one of two things. You can unmute yourself and just verbally ask or write something on the chat. I'll wait for about a minute or two. If there's no questions, then we will sign off. You guys will have, hopefully, for those of you not in my lab, you guys have a good weekend. Stay cool. It's really hot out there. But if there's no questions, then you guys can sign off. Okay. If there is
question.
Yes, what's up?
So when you have a problem about normality with respect to cobalt, so the one that we just worked through,
right?
How do you know that it's talking about charge and not about the number of cobalt molecules? Is that just the definition of normality?
Yes, it is. Exactly.
Okay.
That's just the definition of normality. Normality is equivalence per mole, equivalence per liter. That's normality. And how do we define equivalence? The equivalents are defined in two ways: the charge of whatever species you have, whether it's a cation or anion, or the number of hydrogens or hydroxide that chemical can release. Those are the two ways of defining equivalence.
Got it. So the only time that you would look at the number is if it's hydrogen or hydroxide.
Exactly.
Not anything else.
Not anything else. Perfect. If it's ionic, then you look at the charge.
Got it. And so when it says like with respect to cobalt, you're going to look at cobalt, not the
not chloride. If I said with respect to chloride, then it'll be a -1 charge.
Even though there's two molecules of chloride.
Well, then you have to remember that 1 mole of cobalt chloride is 2 moles of chlorine. Then you use 2 moles of chlorine, and then the conversion factor, one equivalence of chlorine over 1 liter, or one equivalence of chlorine, because it's a -1 per 1 mole. But you have to multiply by 2 because it's coming from cobalt chloride. If it's coming from aluminum chloride, then you would multiply that by 3. You understand?
I think so.
You not only need to know the charge, but how many within that species.
So for the equivalency, if let's say you said with respect to chloride, right, you would multiply by 2, not -1, or not by 1.
equivalents are never negative. Okay,
Okay.
so the fact that it's -1 means it's one equivalence per 1 mole of cobalt chloride. But then you also need to remember that if it's respect with to chlorine, okay, this is it, 1 COCl2, 1 mole, and we're trying to figure out the normality with respect to chlorine. Then you need to remember that for 1 mole of COCl2, you have 1 equivalent of chlorine, but you also got to remember that for every 1 equivalent of chlorine, you have 1 mole of chlorine, you have 2 equivalents here. So therefore, you need to multiply your normality by 2 in order to take care of the fact that you have 2 chlorines. See, if you got like a 3.0 molar COCl2, then you would write it as 3.0 moles of COCl2 over 1 liter. Then you would say that for every 1 mole of COCl2, you have 2 moles of chlorine. And then for every 1 mole of chlorine, you have 1 equivalence. So that's your normality. You see how that works out?
Yes, thank you.
You gotta isolate it. So that's where the 2 comes from. It comes from that formula right there.
Okay, thank you so much.
No problem. Glad to help. Okay. Anyone else? If not, you guys.
Professor, I have
yes.
just one quick question. I don't know if when you're talking about the concentration, it can be any of the things that you said. It can be based on molarity or it can be molality, but it depends how they ask for the concentration.
Exactly. And in lab, you guys are going to be asked a specific way. Calculate the percent concentration, calculate the normality, calculate the molarity. And what you need to do is if you're given information about the solute and the solvent, you have to find the information you need depending on the concentration that you're after to express it in that way. Okay, but certainly there's many ways of expressing concentration. The most popular way, of course, is molarity, but be prepared to calculate the other concentration. Even if I just give you the molarity, you should be able to take the molarity and calculate the molality from that.